So, today we will continue to the topic rate process, and under that we will take up kinetics of some specific reactions. In the last lecture we started with this diffusion controlled reactions. Okay. Now what is this diffusion controlled reaction? Now before that we should consider one thing, the cage effect, that is solvent cage. When a molecule is or molecule or atom or an ion, when it is in solvent phase, then it is surrounded by a cage produced by these solvent molecules. Okay. So that means you have got one molecule over here and you have got another molecule over here. Okay. So like this, two molecules or maybe two molecules, one here, another over here. So they wanted to talk to each other, but maybe they are present in a crowded situation, crowded bus, that in between them there are too many crowds. Too many crowd means too many people are moving around in them. So they are not able to talk to each other. So that means as if this one and this one, these two are caged within, cage, that is cage formed by the other people present within the bus. Okay. So lingering of one molecule near another on account of the hindering presence of solvent molecules, it is called the cage effect. That is, they are inside cage, so they will remain close to each other, but because of solvent molecules in between, they are not able to do any reaction. So they will stay for some time, and then maybe when solvent molecules are moved apart, then they will do the reaction. Okay. Suppose that the rate of formation of an encounter pair AB is the first order in A and B. Okay. So it is an encounter pair. So first order, it say, and this is an elementary process, say, and this is an elementary step. So this is this rate of formation is dependent on this concentration and that concentration. Okay. So therefore A plus B producing AB, which is an encounter pair, encounter complex. Okay. So rate is Kd, okay, times A and B. Okay. Encounter pair rate, I mean formation of encounter, that is that rate. So the encounter pair has two fates, either it will dissociate to give you A and B, or it will react to give you products. Okay. So forward rate is Kd primed AB and the backward rate is Ka. Sorry, forward means dissociation rate is Kd primed AB, and the forward rate, that is product formation, is Kd AB. So net rate of change of AB, because we have to apply the steady state approximation. Okay, that means rate of change of AB, or maybe you can write the rate of change of AB in terms of this forward rate of formation of AB. So it is the production step. Okay, and these two are the it is expending. I mean these are expenditure step, or these are used up. Okay. So that means these two will be with negative sign. So therefore Kd AB minus Kd primed AB for this one, and also minus Ka AB. It is the overall rate of change of AB. AB means the encounter complex. So that means we have to apply the steady state approximation. That means you should put this to be equal to 0. Okay. So steady state, after applying steady state approximation, you get AB, concentration of AB is Kd AB divided by Kd prime plus Ka. So concentration of concentration of AB, okay, because this is the species which is formed and which is used up to give you product. So therefore we have to apply steady state approximation on this species, okay. So that will be equal to Kd A B divided by Kd primed plus Ka. So net rate okay. So product formation rate ddt of is equal to Ka AB, okay, net product formation which is equal to Ka then Kd, okay, Ka Kd then A B divided by Kd primed plus Ka, which is equal to, so these two all together equal to K2. So K2 A B, therefore K2 will be equal to Ka Kd divided by Kd prime plus Ka, okay. Situation 1, that when Kd primed means which step? Let us go back. Kd primed means dissociation of AB back to A plus B. So when Kd primed is very less than Ka, that is Ka product formation, okay, this is very less, then what you can write? So situation 1, that Kd primed is very less than Ka, so that means you can just neglect it, this one, okay. So this will give you K2 is equal to Kd, K2 is equal to Kd, okay. Kd means again the first step, this encounter complex formation step, Kd, okay, and this is called your diffusion controlled limit. Diffusion controlled limit. Why diffusion controlled limit? You can just explain from here that Kd primed is very less than Ka, means this is negligibly small, okay. Just once this encounter complex is formed, it will lead to product, okay. So this is basically a fast step, very fast step, and this is a slow step. Therefore the rate will be determined by the rate constant of the slowest step, that is why it is Kd, and therefore it is called the diffusion controlled limit. So reaction is under diffusion controlled situation, so it is a under diffusion controlled limit. And what happens to the other situation, that Kd, situation 2, primed is very greater than Ka, then what happens? Then Ka, that means this is neglected, therefore your K2 will be equal to Ka Kd divided by Kd primed, okay. So this is called the activation controlled reaction. Activation controlled. Activation controlled reaction, okay. Now again go back to the earlier slide, that Kd primed is very greater than Ka. Kd primed is very greater than Ka means ease of product formation Okay. So, is a product formation is a product formation is you know is a slow step. Okay. So, that means basically this step, okay, this step is very fast, that means diffusing out, I mean once it is formed it will tend to dissociate. So, this is very fast. So, this formation and then you know this you know dissociation. So, this once it is formed it will tend to dissociate. Okay. The situation is you know it is similar to activation process, as if the reaction is passing by an activation barrier. That means you know you have got this AB. Once AB is formed, okay, so this side is your formation of AB, okay, and going back is your you know dissociation, and this is a slow process, okay, that is Ka is low. So, this is similar to a chemical reaction, that is which is occurring via you know via crossing of some activation barrier. Okay. So, what is Kd? Kd is your 4 pi r star dNA, where r star is the distance between the reactant molecules, and d is the sum of the diffusion coefficients of the two reacting species. Okay, where dA is kBt divided by 6 pi eta Ra, dB is similarly kBt divided by 6 pi eta Rb, where eta is the viscosity of the medium, Ra, Rb are the hydrodynamic radius of A and B. And if we assume that Ra is equal to Rb is equal to 1 by half r star is the distance between the reactant molecules, then your Kd will be 8 Rt by 3 eta. Okay. So, what we get is that now a reaction can be called a diffusion controlled when your dissociation process is very less. Okay. So, dissociation process is very less, but like this process dissociation, I mean dissociation of your encounter complex 2 give you back this A and B is less, and the other option, when Kd prime is very greater than K, then it is called the activation controlled. Okay. That means here in this case in the upper case, this first case, it is determined by how fast these reacting molecules are coming close to each other for an encounter complex. That is the you know bottleneck for the process. If it is coming fast, reaction will be fast. If it is coming slow, reaction will be slow. That's why diffusion is the limit. Okay, you cannot reduce it to that, because at least the molecules or the atoms have to diffuse close to each other to do the reaction. Okay. So that's why it is called the limiting situation. Next we will move on to kinetic salt effect. Okay, and it is a thermodynamic version of the activated complex theory. It deals with reaction between ions. Okay, and how does ionic strength affect the rate of a reaction? Does it really affect the rate of a chemical reaction? And if it at all happens, if it at all affects, then how does it affect? So that is the question, and it was first discussed as it was first formulated by Bronsted and Berum, and it is called the kinetic salt effect. That is the effect of salt concentration or effect of salt on rate of chemical reaction. Okay, so how to deal with this? Okay, and of course the question naturally comes, if you have a reaction between two to reactants which are uncharged, then maybe you will not possibly see any effect of salt, possibly. Why it is not that, why you won't see, I will be coming to that point in later part of the discussion. Okay. Now, what does salt do when you add some salt into a solution? It is stated that ionic strength of the medium increases. Ionic strength means it has got some relation to number of ions maybe, but the thing is, if you have say from mono positive ion to dipositive ion, then you say that its ionic strength is more. Okay, it is more because each ion contributes twice compared to the previous case, therefore ionic strength is more. Now, it can be regarded, this ionic strength can be regarded as the average electric field experienced by an ion due to the presence of other ions in solution. It is a qualitative way of understanding what do you mean by ionic strength of the medium. Okay. So, with this thing, let us consider two charged ions A and B with charges Za and Zb respectively. Okay, and they are undergoing chemical transformation to give you some product. Okay, so that means schematically we can write like this: A Za charge plus B Zb charge. Okay, and it will form AB. AB means maybe it is a complex, activated complex with charge, total charge Za plus Zb, and then this activated complex will give rise to product. Okay, give rise to product with equilibrium constant, I mean with the rate constant K double dagger. So, A Za Zb equilibrium, AB, then products. Okay, you can write this as, okay, this is the activated complex. So, rate of formation, what is the rate of formation of a product? Of course, this is the rate constant, this is your rate constant. So, rate of formation dP dt will be equal to, this is rate constant, not the equilibrium constant, K times concentration of this. Okay, and also if it is a bimolecular process, say if it is like it is having rate of formation of product, that dP dt is equal to say K2 AB, then that is for A2 A plus B2 products, then in terms of thermodynamic means the thermodynamic equilibrium constant means can be expressed with the help of your activity. Okay. Now, before that, what is called activity, let us try to understand. Means although for a dilute solution we replace activity by concentration, but it should be actually in true sense we should use activity in place of concentration. So, activity A of some species A is your concentration of A times gamma A. So, this is called your activity coefficient. Okay. Now, this activity coefficient is has got a relation to ionic strength of the medium in the following way, that minus log gamma A is equal to A ZA square root of mu. Mu means ionic strength of the medium, or in some books it is written as square root of I, mu or I, where A is for water 0.509 at 298 Kelvin. Okay. So this is called the Debye-Huckel limiting law for dilute solutions, where ionic strength mu or R I is equal to half summation of Ci Zi square over I. Ci is the concentration and Zi is the charge of the ith ion. Okay. So thermodynamic equilibrium. So for writing the thermodynamic equilibrium constant, we should use this activity. So that means K is equal to activity of AB divided by activity of A into activity of B, which is equal to gamma AB, activity coefficient AB, or maybe AB, okay, into concentration AB divided by gamma A is equal to gamma AB divided by gamma A, gamma B. This is your gamma part, this is your concentration part, B, which is equal to K gamma times this concentration equilibrium constant maybe. Okay. So simplifying this, we can write, rearranging K by K gamma times A times B. Okay. So if we insert this into the rate equation, what do we get? D dt of product is your, we just let us go back to this one, that your K A B. So we'll just put this one, this particular thing over here. So that means K double dagger, then K divided by K gamma A into B. Okay. So rate of product formation can be written in this way. Okay. So this is your equilibrium constant, this is your ratio of the activity coefficients, okay, over here. Now since, as I told you, that for a second order process, dPdt is equal to K2 AB. So overall, if you compare these two, so experimentally observed rate constant K2 has the connection with K double dagger, K and K gamma in this way. Okay. Now we will first start with a very dilute solution approximation. Very dilute solution approximation means that activity A, if we start with this expression into A, then if it is very dilute, then this will tend to unity. So that means for all practical purposes, you can write in place of AA, you can just write A, and therefore your corresponding K gamma, which is your gamma AB divided by gamma A, gamma B. Okay. So this one, that will be equal to 1 for infinitely dilute, therefore it is 0. So for infinitely dilute solution, your K gamma 0 is 1. Now what is infinite dilution? That is, infinite dilution is a solution where you are diluting the solution until you reach the state of 0 ionic strength. Practically there is no ions, at all. That is average electric field experienced by an ion due to other ions. So basically due to other ions means there is no other ion. So it is so dilute, or the thing is that the solution is so dilute that the average separation between maybe two ions is very high, so that practically one ion is not experiencing the influence of other ion, because they are widely separated because of a hugely high dilution, because of a huge dilution. Okay. So therefore you can write K2 0, 0 means infinite dilution is equal to K times K, or you can write what you can write, in place of this you have got K2 is equal to K by K gamma. So your so you can write, so from this you can write again, what you do, you take log of this. Okay. So you have got, and this one is K2 0. Okay, this one is K2 0. So you just replace this over here. Okay. So therefore your K2 is equal to K2 0 divided by K gamma. Now you take logarithm log 10 for both the sides. So log K2 is equal to log K2 0 minus log K gamma. Okay. So this one is your situation of infinite dilute case. Okay. Now you put the expression for K gamma. What is K gamma? K gamma is this. K gamma is your gamma AB. Here you should write 0. Gamma AB divided by gamma A, gamma B. So you write log K2 0 minus log gamma AB, gamma A, gamma B. That means you can write from this, you can write log K2 is equal to log K2 0 minus log gamma this plus log gamma A plus log gamma B. So if we incorporate the respective expression of Debye-Huckel limiting law, then we will be getting, because log gamma is minus A z square root of ionic strength. Therefore in place of this you can write log K2 0 plus A, because A is a constant. Okay. So ZA plus ZB whole square minus ZA square, because ZA plus ZB whole square, because this is the overall charge of this state, this activated state, minus ZB square root of ionic strength. Okay, so log K20 minus A, then this is ZA square plus ZB square, so these two will get cancelled, so 2 ZA ZB, okay, square root of ionic strength. Okay. So, this is the expression that relates your rate constant for the reaction at a given ionic strength, rate constant when ionic strength is 0, and this is ionic strength of the medium. So, if we plot log K2 versus square root of ionic strength of the medium, we should be getting a straight line. We should be getting a straight line of this, because it is a plus, okay, like this, and your intercept slope will be giving you this one, a 2a z plus z minus, and intercept will be giving you log K20. That is that means when you extrapolate this to 0 ionic strength. Okay. So, from here you are extrapolating, okay, this up to this you are extrapolating maybe, okay, because you cannot in principle make a solution containing ion, but ionic strength is 0, because we are discussing ionic reactions. Okay. Okay. So, this is a a linear dependence on this square root of ionic strength. Now, in fact, this expression predicts the effect that an increase in ionic strength will have on the rate of reaction involving ions. So, for ionic reactions, if we increase the ionic strength, then what is going to happen to the overall reaction rate, or rate constant rather. Okay. Now, for water at 25 degree centigrade, 298 Kelvin, if we put the numbers, then log K2 is equal to log K20 plus 1.018, because 0.509 is A, 2 into 0.509 means 1.018. So, ZA ZB square root of I. Okay. So, log K2 by K20 is equal to 1.018 ZA ZB square root of I. Okay. So, from this means if we plot log K2 against square root of ionic strength, the slope will be this, and this is obtained, and from which the charge on ions and on the activated complex can be calculated, can be determined experimentally. Okay. So, this is a typical plot for that is showing the salt effect, that log K2 is log K20 1.018 ZA ZB square root of ionic strength, where log K2 is C intercept and m is slope. When m is equal to plus 1.018, it is the positive slope. When it is minus, it is the negative slope. Okay. For 1 case, plus 1 or plus 1, or minus 1. Okay. So, same type charge means plus means it is plus, so it will increase. Okay. Minus it will increase, but if it is opposite 1 plus 1 minus, then it will be minus over here. So, that means this situation will come, and when either of two ions is having 0 charge, then it will have no effect. Okay. So, charge on this, okay, if this is this will be charge on AB. Okay. Here it is plus 2 or minus 2, plus 1 or minus 1, and it is 0. Okay. So, these can be determined from whether this charge of AB is both plus or both minus, or maybe one plus, I mean overall charge, whether overall charge is plus, overall charge is minus, that you can determine from the nature of the plot. Okay, because it is basically your it is the difference, you see, if you look into the derivation, you see that it is ZA square ZB square, and ZA ZB is the overall charge on the activated complex. So you can find out in principle the charge on AB from this particular plot. So kinetic salt effect has got immense importance. Okay, there is again go back to another slide that you see that here you see, if we plot log k by k0, what I was trying to explain in last slide. Okay, that is that is last slide means this one. It is again demonstrated over here. Let us go back to another slide. This one, it is a plot of log k by k0. Okay, so you see what is going to happen. So if it is plus 4, that is 2 plus 2 plus, it is plus 4. You see it is a huge slope, positive slope. Okay, 1 plus another 2 plus intermediate, that is 2, overall 2, it is 4, plus plus means 1, so lesser slope. Then this is plus 0 or minus 0, 0, again 1 plus 1 minus, negative, it is 2 plus 1 minus, still negative, 2 plus 2 minus, minus 4 basically. So you see that it is the test of test, means you can test that whether effect of salt is there in a kinetic process, and especially when we consider ionic species in solution. Okay, now what is happening here, that if you increase your the ionic strength, what is going to happen? Why your rate is increased, I mean rate constant is increased. Rate constant means ultimately rate is increased, because the system is passing through a transition state, that is a transition state or an activated complex of this sort AB ZA plus ZB, this one. So it is a charged species. Okay, so if this is a charged species, say suppose this species does not have any charge, say for example, suppose ZA is 0, ZB is also 0, then this species will not feel any electrostatic interaction, that is its overall energy is not getting modified, even say one is plus 1, another is minus 1. Okay, so one is plus 1 means suppose we have got say one ion, say here, another ion here, so one is plus 1, another is minus 1, say, that means it is like a dipole. Okay, so dipole is you are immersing a dipole, where you are immersing a dipole in an ionic solution. So there will be effect, there will be interaction between this dipole, because it may act as a dipole, this AB, this species may act as a dipole, because one part is plus, another part is minus, so it is a plus minus case. So its energy level will be affected. So that means this transition state will be influenced in presence of ions. If the transition state is influenced by ions, then what is going to happen? What is going to happen? That if transition state is influenced, then if you look into this diagram, that like this, your reactant, this is your product, okay, and say this is your activated complex, say one is plus, another is minus, so it is a dipole. Okay, so its energy level will be modified. Okay. And how much it will be modified, it depends on, you know, whether, means how this is also modified, this state, because this state is typically your one plus charge, one minus charge, they were initially separated. So this will be stabilized, this will also be stabilized. Okay. Now it depends which one is more stabilized or which one is more destabilized. So therefore that will determine the overall change in activation energy. Okay. So it is because of your because of the change in this state, or maybe this state, that is responsible for changing your overall activation energy of the process, and rate is, hence it is modified. Suppose if it is one is plus, another is 0, that means you started with one state of your starting state, your reactant is plus 0 and your transition state is also plus 0. So it is nothing new, means nothing new means if you change the ionic strength of the medium, then these two will be similarly affected compared to these two. That is, if you compare these two will be, so this is your transition state and this is your reactant state. So these two will be similarly affected. If it is destabilized, both will be destabilized to same extent. If it is stabilized, both will be stabilized to same extent. So therefore no net change in the between change in energy state between these two. Therefore there will be no effect. That is why you see, if you look into this one, you see if it is plus or minus, you will be seeing that no effect of ionic strength. When it is plus plus, it is increasing. When it is plus minus, it is decreasing. Okay. So this has got a tremendous importance. So when specially you consider ionic reactions, so this is of immense importance. So you see that how your ionic strength of the medium. So as I told you, ionic strength is a measure of average electric field experienced by an ion due to the presence of other ions in solution. So since it is a chemical reaction of ionic species, so you know, electric field experienced by ions, that is reacting ions, and your transition state could be similar or could be different depending on their charge nature. If they are similarly affected due to the presence of ions, then we do not see any effect on rate constant. But if they are differently affected, say one is destabilized, another is destabilized but to lesser extent, or maybe in some other way, then you will be seeing that the rate of reaction and the rate constant is affected, you know, tremendously. So it is the basically a consequence of electrostatic interaction between the ions in solution. And this 0.509, this A, which is 0.509, this is for water at 298 Kelvin. Okay. If you take a different solvent, then you have to consider, you know, A, that is you have to use a different value for that solvent, and also temperature is a very important factor. Okay. Because temperature, if temperature is increased, so average thermal motion of ions and ions in solution will also be affected. Therefore that may influence, I mean for sure that will influence the overall rate of reaction. Okay. So here we have made use of Dilution limiting law, okay, to find out this ionic strength in terms of concentration and the charge on ion. And of course one thing we must consider, that this limiting law is for dilute solution, it is not for concentrated solution. So for concentrated solution, this expression of ionic strength is different. Okay. Therefore whatever kinetic salt effect on ionic reactions I have discussed over here, it is for moderately or maybe for dilute solution. It is not applicable for concentrated solutions, because for concentrated solution you cannot apply ionic strength in this way, that is I is equal to half summation of Ci zeta square, not that one, I mean log gamma plus gamma A is equal to A z plus square root of I, that you cannot use. Okay, that means the relation between log gamma and ionic strength will be different. It is not linear. Okay, so therefore this kinetic salt effect is for pretty much for dilute solutions. Okay, so what we have learnt here in this particular part, here we have in a particular part, especially kinetic salt effect, it is the thermodynamic version of activated complex theory. That is it is the formation, it deals with the formation of an activated complex due to interaction of two ions. It may be similar charged, may be differently charged, similar, I mean plus plus, plus minus, or maybe minus minus. Okay, so and it deals with reaction between ions, and how does ionic strength affect the rate of reaction is the main concern of this particular topic, that is kinetic salt effect of salt on kinetics of a particular reaction. Okay, so here what we have done is that we have taken two ions, okay, and we have formed the activated complex which is in equilibrium with the ions, constituent reactant ions, and then this AB this activated complex that undergoes chemical reaction to produce your desired products. Okay, and in a separate way we have also used this formula that dPdt is K2AB. So, you have compared this rate and that rate, because these two rates must be equal, because we are discussing the same reaction, and from that we have used the activity concept, because activity concept is useful when the solution is concentrated, but for dilute solution you can use concentration. Okay, and then we have made use of the Debye-Hückel limiting law to find out, to simplify this equilibrium constant. Okay, and it turned out to be like this, and finally it gave this expression, this simple expression that rate constant at 0 ionic strength and your log k gamma, that is the ratio of the activity coefficient. Okay, ratio of the activity coefficient. So this is a very simple relation, this is a very simple elegant relation, and if we simplify it, then we will be finding that log k2 is equal to log k2 0 plus this factor. So, this factor is the factor that is responsible for the modification of your rate constant with ionic strength. This is responsible for this. So, therefore, and you see that since it is in plus sign, so ZA plus ZB, if these two are in same sign, then it will be in plus sign. So, if your reacting ions are, say, both of them are positive, or if both of them are negative, then the rate constant will be increased. Okay, rate constant will be increased as you increase the ionic strength of the medium, as you increase the average electric field experienced by ions due to the presence of other ions in solution. Okay, so it will increase with a positive slope, and if you have Z plus Z minus, product of Z plus Z minus negative, then it will reduce. That means as if the increase of ionic strength has got an opposed effect. It tends to slow down the process. It doesn't favor. Somehow your activated complex is maybe destabilized. Okay, and if it is destabilized, so if activated complex is not formed, so how does the reaction means how can the reaction proceed? Okay. Okay, so and if we plot we can find out the type of what is the overall charge of the activated state. Okay, and this is a typical plot, and if we take this plot, this gives you a nice idea of 2 plus or 2 plus plus or plus plus or plus minus, or I mean plus 0 or 0 minus. Okay. So, in this particular section, section where we dealt with kinetics of some specific reaction, especially this ionic reaction. Okay. So, how these ionic reactions are affected due to presence of other ions in solution. That is a very important part that we have taken up, and we tried to explain. And also we discussed this diffusion controlled reaction. Okay. Now, diffusion controlled reaction means the reaction the rate which is dependent upon how easily or how fast these reacting species are diffusing and coming close to each other. So, that is the determining factor for the process. Okay. So, that is a very important aspect which we also have talked about. So, diffusion controlled reaction falls under fast reaction. Okay. And there are plenty of examples that you will be finding in literature, okay, that in connection with salt effect, and that demonstrates that if you change the salt concentration, ultimately there is enormous effect on overall rate of reaction. Overall rate of reaction means how fast the products are formed. Okay. So, therefore, like temperature is a very important parameter for chemical reaction. If you increase the temperature, since reactions which we already have talked about, normal reactions, okay, or any reaction, these are if the reaction is energy barrier dependent, then if you increase the temperature, then rate will change and rate will increase. You will never find that rate get reduces. Okay. In the same way, like temperature, for ionic reactions, ionic strength is a very important factor. Okay. That may in principle change the rate constant. Okay. Because states are modified in presence of ionic strength. Your starting state, and then your activated state and your final state, all are modified. Their relative positions are modified. Therefore, the system is no longer identical to the initial situation when there was no added salt. That is why it is behaving in a different fashion, and rates are modified. I mean, rate constants are also modified. Therefore, we will continue in the next lecture. We will continue with kinetics of some specific reactions, and then we will take up kinetics of catalyzed reactions, especially enzyme catalyzed reaction we will take up. Okay. So, till then, have nice time. Thank you.